So hello everyone, today we'll be discussing questions on alternating series. There were five questions asked on this topic, so let's just see them one by one. So the question 1 says that find the range of P for which this given series, let's name it as UN for time being, is absolutely convergent, and second part is conditionally convergent. So they have given us a series as summation un, which is equals to summation 1 upon minus 1 raise n plus 1 upon n plus a raise p, and this p is unknown. So we are supposed to tell for what values of p the series is absolutely convergent and for what values of p the series is conditionally convergent. Also in the question they have given us that the p is greater than 0. So we are supposed to check for all those p for which p is greater than 0. So first let's move on to see the absolute convergence. So first part is absolute convergence. So the absolute term series of this will be, like absolute term will be 1 upon n plus a raise p. Now if I assume another sequence, let name as vn, let vn be another sequence as n raise p. Now if I use limit comparison test, then this will give me limit n approaches infinity mod un over vn. So what will it give? It will be limit n approaches infinity n raise p divided by n plus a raise p. Now if I solve it, I'll get the limit as 1. Now we know that limit comparison test says that if this limit, that is limit comparison test, says that if the summation un and summation vn are two series and limit n approaches infinity, un by vn turns out to be L, which is not equals to 0 and it is a finite number, then both of the series, that is both summation un and summation vn, behaves alike. There are like results based on value, like if L turns out to be 0 and L is infinity, that we don't need in this question, so we'll see that later. So since 1 is a non-zero number and also it's a finite quantity, so from this test we can conclude that summation mod of un and summation vn will behave alike. And since summation vn is a p series, so we know its behavior. So it converges for p greater than 1 and diverges for p less than or equals to 1. So since vn and modulus of un behave alike, so from here we can conclude that summation of mod un will converge for p greater than 1 and it will diverge for p less than or equals to 1 and will diverge for p less than or equals to 1. So this completes our first part. So range in first part is, range for absolute convergence is p greater than 1, that is p belonging to 1 to infinity. Now let's move on to see the second part, in which we are supposed to find out the range in which the given series summation un is conditionally convergent. Now first we should know what is the meaning of conditionally convergent, and then we'll move on to see the question. So we say that a series a series is said to be conditionally convergent. Let's name our series something. A series summation an is said to be conditionally convergent if the series summation an converges, but the series formed with absolute values, but the series that is summation mod an diverges. So that means that a series is conditionally convergent if it is convergent, but it's not absolutely convergent. So in the first part we have seen that our series is absolutely convergent for p greater than 1. So in this case, we basically from the part 1 we can derive that we are supposed to check, like we only need to check for all those cases where p is less than or equals to 1. We need to check cases where p is less than equals to 1, because the condition for conditionally convergent is that the series should not be absolutely convergent, and from the first part we got that it's not absolutely convergent for p less than or equals to 1. Now if you observe that our series is summation un is minus 1 raise n plus 1 divided by n plus a raise p. This is our value, and we know that like there is a test, that is Leibniz test. Let me just recall that test. Leibniz test, and it is a special test for alternating series, and this test says that if summation mod 1 raise n plus 1 bn is a series such that first condition is limit n approaches infinity bn is equals to 0, and second condition is bn is basically a decreasing sequence. Then our series is basically convergent. Then summation minus 1 raise n plus 1 bn is convergent. So we'll be using this test to check our convergence of our given series. First let's see what is our bn in this case. So bn will be 1 by n plus a raise p, and if we calculate its limit, so limit n approaches infinity bn will be basically 0. So our condition 1, that is this one, is satisfied, and we are supposed to check condition 2, that is we are supposed to check if our term bn is basically forming a decreasing sequence. So in order to prove that this is a decreasing sequence, let's just calculate its derivative. So that will be derivative of, minus of p divided by n plus a raise p minus 1, and this term will be always less than 0 because my n is positive, a is positive, so all the terms are positive, and because of this negative term sign, this whole thing will be negative. So from here I can say that my bn is a decreasing sequence. Also you can do it in other way as well, because we know that n minus 1 plus a will be less than n plus a, and from here n minus 1 plus a raised power p will be less than n plus a raised p, and from here we can conclude that 1 by n plus a raised p will be less than 1 by n minus 1 plus a raised p, and this is nth term, that is bn is less than bn minus 1, but n is greater than n minus 1. So from here we can conclude that our sequence bn is a decreasing sequence. So by Leibniz test, we can conclude that by Leibniz test we conclude that summation un is convergent when p is less than or equals to 1, but it's not absolutely convergent, not absolutely convergent in that domain. So the domain for part B is p less than or equals to 1 and greater than 0, because that's given to us in question. So let's move on to see the next question. So the next question says that, oh, it's a repeated question, the same question they have asked again. Repeated question. This time they have specified the range of p in the question itself, and we are just supposed to check whether it holds or not. So let's move on to see the next question. This question says that prove that an absolutely convergent series is convergent. This is the first part, and in the second part they have given us a series and we are supposed to show that it is conditionally convergent. So for proving absolutely convergent, we'll be using a limit comparison test. So comparison test only. So the comparison test says that if summation an and summation bn are two series such that an is less than or equals to bn for all n belonging to natural number, then if summation bn is convergent implies summation an is convergent, and second part is if summation an is divergent, so that implies that summation bn is also divergent. Now in order to prove that absolutely convergent series is convergent, let's consider a series. So let us assume that un be any arbitrary series and we know that our absolute value function has this property that for any x is less than or equals to modulus of x. So using this property for this given series un will be always less than or equals to modulus of un. So basically we have compared a series un with its absolute value series, and in the question it's given that series un is absolutely convergent, and comparison test says that if this series is convergent, that means that the other series is also convergent. So from here we have concluded that summation, that means that summation mod un is convergent, and while comparison test we got that summation un is also convergent. So from here we got that absolutely convergent series is convergent. You can use another way as well to prove that its absolute convergent series is convergent, because if a series is absolutely convergent, then mod an, let's say our series is summation an, then mod an will converge to, let's say, mod a. So you will get this term as less than epsilon, and you can use like this term an minus a will be less than or equals to this term, so you can use this relation as well. So you can go by any way, whichever you like. Now let's test the convergence of given series. So the series given to us is 1 minus 1 by 2. So the series is 1 minus 1 by 2 plus 1 by 3 minus 1 by 4 and so on. So if I name it summation un, so it will be summation minus 1 is n plus 1 divided by n. So this is a given series, so we'll be using Leibniz test again. Leibniz test. So in this case our Bn is 1 by n, and limit n approaches infinity, Bn is basically 0. Also Bn is a decreasing sequence because n minus 1 is always less than n, and from here 1 by n will be less than 1 by n minus 1. That basically gives me Bn is less than Bn minus 1. So therefore Bn is a decreasing sequence. So by Leibniz test, our given sequence, that is summation minus 1 raise n plus 1 by n, is a convergent series. Now I guess we are supposed to check for absolute. Okay, we are supposed to show that it's conditionally convergent. That means like we are also supposed to show that it's not absolutely convergent. So the absolute value of this series will be this, and it will be equals to summation 1 by n. Now this is basically a P series, and we know that P series is convergent if P is greater than 1 and divergent if P is less than or equals to 1. In this case our P is 1, so from here we can say that summation 1 by n is a divergent series. Therefore our given series, that is summation minus 1 raise n plus 1 by n, is absolutely convergent, is convergent but not absolutely, is convergent but summation 1 by n is divergent. Thus the original series is, it's conditionally convergent. Now let's move on to see the next question. So the next question is, show that the series, that is this, is conditionally convergent, and if you use any theorems to show it, then you must give a proof of the theorem. So this is the series that we just discussed. So we have just proved that it is conditionally convergent. Now since we have used the Leibniz test here, so we'll give proof of Leibniz test. So proof of Leibniz test. So the Leibniz test says that let summation n equals to 1 to infinity minus 1 raise n plus 1 un is equals to, it will be un minus u2 plus u3 minus u4 and so on, plus minus 1 raise, let's make it n minus 1, n minus 1 un and so on, and here each un term is greater than 0 for all n belongings to natural number, and this series un satisfies certain condition. First is un plus 1 is less than or equals to un for all n belonging to natural number, and second thing is limit n approaches infinity, un is equals to 0. Then our series, that is summation minus 1 raise n minus 1 un, n varies from 1 to infinity, is convergent. That's the statement of Leibniz test. Now we need to prove it. Now first thing that we should do is, let's just define two subsequences, that is S2n. So it will be u1 minus u2 plus u3 minus u4 up till u2n minus 2, u2n minus 1 minus u2n. Likewise s2n plus 2 will be, or let's say s2n plus 1 will be u1 minus u2 plus u3 minus u4 up till minus u2n plus u2n plus 1. So if we just find out its difference, that is s2n plus 1 minus s2n, so it will turn out to be u2n plus 1, which is greater than 0, because each un term is greater than 0, and like that's the necessary condition. So from here we got that s2n plus 1 is greater than s2n, and so this basically gives us that our sequence of partial sum is monotonically increasing. Now again, if we calculate s2n, so that will be u1 minus u2 plus u3 minus u4 up till u2n minus 1 minus u2n. So can I write it like this? u1 minus, I'm just pulling out minus sign from all the left equations, so it will be u2 minus u3 plus u4 minus u5 plus so on minus u2n minus 1 plus u2n. So it will be equals to u1 minus, we are just clubbing two terms together, these two terms. Before this term there will be u2n minus 2 as well, so we are clubbing these two terms together and we'll be only left with u2n. So this term can be written as u2 minus u3 plus u4 minus u5 so on plus u2n minus 2 minus u2n minus 1 plus u2n. Now if somehow we can show that this term is basically a positive term, this whole term is a positive term, so then we can conclude that this whole thing will be less than u1. But the initial condition for the necessary condition is that this series un should be decreasing. So that means since un plus 1 is less than un, so that means un minus less than or equals to, so that means un minus un plus 1 will be greater than or equals to 0 for L belongings to natural number. So from here we can conclude that u2 minus u3 and u4 minus u5 and so on up till u2n minus 2 minus u2n minus 1. All these terms will be greater than or equals to 0. Also the necessary condition is that each un term is strictly positive. So that basically gives me u2n is strictly positive. So this whole term, that is u2 minus u3 plus u4 minus u5 up till u2n minus 2 minus u2n minus 1 plus u2n, this term will be strictly greater than 0. Even if these terms turn out to be 0, this un term is strictly positive, so the sum of all these terms will be strictly positive. So from here we can conclude that our s2n is less than or equals to u1, and it holds for all n belonging to natural number. So from here we got that our s2n is bounded above by un, and we have earlier proved that it is basically s2n, it is a monotonically increasing sequence. Since a monotonically increasing sequence which is bounded above as well, so it is convergent. So from here we can conclude that our s2n is a convergent sequence. It's a convergent series. Sorry, it is because it is sum of all the terms. Is a convergent series. Now let's assume that this converges to something as s. Let limit s to n is equals to s, n approaches infinity. And also the necessary condition is limit n approaches infinity, un plus 1 is equals to 0. So if we just calculate it, so from here we'll get that limit n approaches infinity, s to n plus 1, so it will be equals to limit n approaches infinity. S to n plus 1 is s to n plus u to n plus 1. So it will be equals to limit n approaches infinity s to n plus limit n approaches infinity u to n plus 1. This term tends to 0 because of the necessary condition of the Leibniz rule, so it will be equals to limit n approaches infinity s to n, and we have assumed that this limit is equals to s. So from here we got that limit of, if limit of even terms is s, then limit of odd terms is also s, that is s to n plus 1 is also equals to s. So this basically give us that s to n and sequence s to n plus 1 converges to same limit. Converges to same limit. Now we are supposed to show that the whole sequence converges to this limit s. Now our claim is the whole sequence, that is Sn, is convergent and it converges to s. So the sequence Sn, that is sequence of partial term of first n term, so it will be u1 minus u2 plus u3 minus u4 up till minus 1 raised n minus 1 un. So it will be equals to this. So now let us assume that epsilon greater than 0 be given to us. Now since we have shown that these and these two sequences are convergent, so if we just write their definition, so what we'll get is, for given epsilon there exists some p belonging to natural number such that modulus of s to n minus s is less than epsilon for all 2n those are greater than this p that we have chosen, that we got. And likewise if we write convergence definition for s to n plus 1, so what we'll get is, and there exists some q belonging to natural number such that modulus of s to n plus 1 minus s is also less than epsilon for all 2n. Let's name it as 2n minus 1 because then it will be convenient for us. 2n minus 1 greater than q, that is for all 2n those are greater than q plus 1. So if we take our n 2n to be maximum of, let's say, p comma q plus 1, so from here we'll get that modulus of s to n minus sn will be less than epsilon for all 2n that are greater than this. Let's name it as p. For all 2n those are greater than this p dash, let's name it as p dash. So from here we got that s to n is convergent and it converges to s. And since S2n is basically sequence of partial sum of the series that is given to us, so from here we can conclude that this summation un, the original series, that is summation minus 1 raised n minus 1 un, is also convergent, and it converges to S. It also converges to S. So that basically completes our proof. So what we have done is we have used the given conditions, that is the decreasing term condition and this limit condition, and we have shown that its sequence of partial sum is convergent, and further we have shown that it's all the sequences of partial sum, whether be it of odd terms or even terms, they will converge to same limit. And then based on that we have concluded that our series is also convergent and it will also converge to S. Now let's move on to see the next question. So the next question says that test the convergence and absolute convergence of this given series. So again it is an alternating series, so it is summation n equals to 1 to infinity minus 1 raised n plus 1 n divided by n square plus 1. Now if you observe this term bn, so our bn is n divided by n square plus 1. Now first let's just find out its limit. So limit n approaches infinity, bn will be equals to limit n approaches infinity n divided by n square plus 1. And if we just solve it, we'll get limit n approaches infinity 1 by n divided by 1 plus 1 by n square. And if we calculate its limit, it will turn out to be 0. So the first condition is satisfied for the Leibniz rule. So second condition is this bn should be a decreasing sequence. So if we calculate bn plus 1 minus bn, so that will be n plus 1 divided by n plus 1 square plus 1 minus n divided by n square plus 1. So it will be equals to n plus 1 times n square plus 1 minus n times n plus 1 square plus 1 divided by n square plus 1 into n plus 1 square plus 1. So it will be equals to n plus 1 times n square plus 1 minus n times n square plus 2n plus 2 divided by n square plus 1 times n plus 1 square plus 1. And if we just simplify it, it will be n cube plus n square plus n plus 1 minus n cube minus 2n square minus 2n divided by n square plus 1 into n plus 1 square plus 1. This n cube balances this one, so we will be left with minus n square minus n plus 1 divided by n square plus 1 n plus 1 square plus 1, and it will be less than 0 for all n belongings to natural number. And you can check that as well, because in natural number n is always greater than or equals to 1. So from here we can conclude that n square is also greater than or equals to 1. So n plus n square will be always greater than or equals to 2. Minus of n plus n square will be less than or equals to minus 2, and if we just add in 1 both sides, so it will be 1 minus n plus n square will be less than or equals to minus of 1, and the term in the denominator will always be positive, so this whole thing will turn out to be less than 0. So that basically gives me that my bn plus 1 minus bn is less than 0. Less than 0. So from here I can conclude that bn plus 1 is less than bn. So that basically gives me that the sequence bn is a decreasing sequence. And by Leibniz test, since both the necessary conditions are satisfied, so I can just use the Leibniz test. So by Leibniz test, I'll get that my series summation minus 1 raised n plus 1 bn is convergent. Now we're supposed to check absolute convergence as well. So the absolute term series of this will be summation n divided by n square plus 1. Let's name it as summation mod un. Now let's assume another series, that is summation 1 by n. And how do we know like which series should we compare? If you observe that this sequence is similar to summation n divided by n square, that is 1 by n. So you can just get an idea like via this method with which series you should compare. So if we just use comparison test, limit comparison test, that is limit n approaches infinity, mod of un by un, so it will be limit n approaches infinity, mod un is n divided by n square plus 1 and bn is basically 1 by n. So it simplifies to limit n approaches infinity n square by n square plus 1. That will be equals to, like if we just calculate its limit, it will be equals to 1. And 1 is not equals to 0. Also it's a finite quantity. So by limit comparison test, we got that summation mod un and summation mean, both these series will behave alike. And we know that this summation 1 by n being p series is divergent, because p series is divergent for p less than or equals to 1, and here our p is 1. So from here we can conclude that our series, that is summation mod un, is also divergent. So from here we got that our series summation un is convergent, but summation mod un is divergent. That means that summation un is conditionally convergent. That completes our questions on alternating series. So there are only these many questions. So from here you see that you're also supposed to see the proofs of important results, because they can ask anytime directly to solve it, and it will be difficult in exam to solve it from scratch. So it's better to look up for proofs while reading the theory portion. So thank you for watching, and please do like, share and subscribe the channel.